Hello and welcome to another webinar for LabV. My name is Charles
I'm Stefan.
and we're both the co-founders of LabV. And today we would like to share with you our current experience working with machine learning. The webinar is, as usual, going to last approximately 40 minutes, 45 minutes. And you'll have the opportunity at the end to ask some questions using our Q&A function. Just for your information, this webinar is currently being recorded and is going to be available online on demand just within a few hours after. So what do we want to do today? We actually want to understand what machine learning is, understand its benefits. We want to explain how it works with the use case from our customer base and share with you our learnings as of today. For those who don't know who LabV is, LabV is a company of the Net Group, and with our material intelligence platform, we support R&D and quality engineers in the development and manufacturing of better products by eliminating inefficient data, processing and management. We deliver targeted insights from relevant data to enable all these specialists to do informed and data-driven decisions. If you're here today, it's probably because you're looking for, and it doesn't matter if you're working in R&D, process engineering, in the lab, or in quality control, you're probably looking for either more efficiency, where you want to save time by removing your non-value adding activities, automate some of the recurring tasks you have to do, or you're looking for better products, you want to make database decisions. You want to have better performing materials and at the end product. You may be looking for more innovation, shorter time to market cycles, a greater competitiveness, and at the end more turnover. Or maybe it's about the knowledge and you want to secure the expertise within your organization and improve cross-department cooperation. Maybe it's all four. These are the challenges and basically the goals that company want to achieve in this year. And machine learning and artificial intelligence are both playing a very important role in that. So what's the difference between AI and machine learning? Let's say that artificial intelligence, or AI, as I'm going to call it further, is like the big umbrella. It's about making machines simulate human intelligence. It can involve rules, logic, and learning. And on the other hand, machine learning is more of a subset of AI that focuses on learning from the data. So think of AI as the entire field, like the concept of an automobile, while ML is more a specific technique like an electric engine. So not all AI uses machine learning, but all machine learning is part of AI. The official definition based on the National Artificial Intelligence Act in the USA from 2020, the term artificial intelligence means a machine-based system that can, for a given set of human-defined objectives, make predictions, recommendations, or decisions influencing real or virtual environments. So that's the official definition. The official definition or the description of machine learning coming from Tom Mitchell in 1997, which is like kind of the father of machine learning. A computer program, so how to describe machine learning, it's a computer program that is said to learn from experience called E with respect to some class of tasks, T, and performance measure, P, if its performance at task T as measured by P improves with experience, E. So let's break it down and use easier, simpler words. Machine learning is a method where the computer learns patterns from data instead of being explicitly programmed with rules. The more data they process, the better they become at a specific task. If I break it down in this definition, E, so the experience, is the data the system is learning from. Think of it as, for example, historical test results or historical performance data of a formulation in your lab. T is the task. It's the specific job the model is learning, like predicting the best material composition for a new formula. And P is the performance, so how well the model does its job, measured by the accuracy, maybe the error rates, or even the reliability. So let's say you're testing a new coating formulation. Instead of manually comparing dozens of past results, a machine learning model can analyze all the historical data and predict with which combination is likely to perform best under very specific conditions. It learns patterns from the past and from past experiments and improves as more data is added. So machine learning is not just automation. It adapts, it's improving, and it finds patterns in very complex data. The more experience it has, the better decisions it can help us make. We brought you some of the our everyday experience examples here. So if I take the example of ChatGPT, which you may have seen or used before, ChatGPT is a good example for AI. It's generating human-like text and responding to questions. But how does ChatGPT improve? That's where machine learning comes in. ChatGPT has been trained on a huge amount of text and keeps improving based on every user interaction. That's the machine learning part. If you take facial recognition, when you unlock your phone, for example, unlocking your phone with the facial recognition is an AI application. Machine learning is playing a role when your phone gets better at recognizing your face over time, even with different, for example, lighting or angles. Another one, spam filters. Your email provider is using AI to filter spam, but machine learning is making it better over time. Or even another one, self-driving cars. The self-driving car is based on AI, it's following programmed rules to drive, but machine learning is what's allowing the car to learn from real-world driving experiences, improving the safety and also the decision-making at the end. So AI is kind of the broad concept of intelligent behavior, while machine learning is actually how many AI systems improve over time by learning from the data. The more experience it has, the better its performance. Because you're all very technology oriented, we thought we would give you some of, describe the building blocks of machine learning. So it sounds very complex when we define it. I think the example are helping a lot, but it's following a very structured process. The building blocks are always the same. Instead of programming a machine with very strict rules, we actually teach by providing the data, training the model, and letting it learn from patterns on its own. So let's break it down building block by building block. First, you need the data. It's the foundation. Everything starts with the data. The quality, the quantity of the data is determining how well your ML system is going to perform. The system learns by analyzing historical data and identifying patterns. The second block is the features. Not all data points are equally useful. We extract the relevant characteristics, they are called features, that help the system recognize the patterns. And once we've done that, we use that in a model. The model in the algorithm, it's basically, the model is what's making the predictions. So it's built using an algorithm, which is a set of instructions that guides how the system learns from data. Different algorithms work usually in different ways, but they all aim to improve the performance over time. Then we have to train it. During training, the model learns by adjusting itself based on the data. The goal is here to minimize errors and improve the accuracy. Once we have trained, we have to evaluate the system. We test the model using new data to see how well it's performing. This step is actually the one that ensures that the model isn't just memorizing, but actually learning patterns. And there is one last step or one last building block, which is the prediction. Finally, when the model is trained, it's used to make the actual predictions. The more data it processes, the more accurate and reliable it becomes. So let's go back to one of our examples here to make it very tangible. If I take the example of spam detection, you all use a email client, you all receive and send emails every day. And sometimes you may wonder why you didn't get an email from a colleague and it's been filtered or detected as a spam from your, for example, Outlook, right? When we talk about the data in our spam detection, to train a spam filter, we need data. It's millions of past emails that are labeled as spam or not spam, right? The features, while not all email content matters, the system is actually extracting only useful features like the words or in the subject line, or the links in the text, maybe the sender reputation, if there is such a thing, or even the attachments. Then the model is going to learn patterns. For example, if an email is containing something about winning a free iPhone, and it comes from an unknown sender, it might be spam. Based on that, we train the model, and it's trained to analyze thousands of emails. Over time, it's refining the decision making by adjusting which features matter the most. Right? We evaluate the model before rolling it out. So we test the model with brand new emails, and we see how well it's identifying spams. And finally, it's making prediction. So it's actually used in your inbox. And when a new email is arriving, the trained model is predicting if it's spam or not, automatically filtering suspicious messages into the junk folder. So that's basically what happens if your colleague or your family send you an email and you don't find it, it's in the junk folder. The reason is because basically your algorithm thought it would be spam based on some of the features inside it. Now you may wonder, what do we do with that? Why is it relevant for us as R&D or quality engineers? Well, using machine learning in our field has very different benefits. First of all, it enables faster decisions. And applied to our situation, we talk about faster material testing and even faster material formulation development. You can reduce your trial and error cycles. You can accelerate R&D using machine learning. We improve the accuracy. If you remember, we talk here about reducing the errors by learning from large data sets. Well, it's the same. The more you learn, the less errors you're going to make, which means, for example, in quality control, you could identify potential defects right before they occur, and by doing so, improving your product quality. You can automate repetitive tasks because you free up the human time for complex work. The human brain is not designed to identify complex patterns and deal with a large amount of data, which means in R&D, in the lab, or in quality control, we could eliminate manual data entry, reduce the errors, and save time in general in the whole evaluation of the data. Very, very important. Machine learning helps you find hidden patterns, which means you could reveal actually unseen material relationships, uncover links between formulations, processing parameters, and even performance outcomes that you haven't seen before. And finally, machine learning is a good way, a good technology to adapt and learn over time, which means you can make, for example, better predictions in R&D using past results or test data to recommend promising formulation. But now let's go into a concrete use case.
So what does that all mean for the development of materials? What we have as a use case is a use case from the paint and lacquer industry. But before we go into the use case, let's first of all look at which approaches actually do we know in material development. Because we can distinguish three basic approaches, and machine learning is one of them. The classical, I would call it the classical approach, is more or less the experimental approach. You do experiments more or less on a trial and error basis to discover a new material. Most of the time you change then one factor at a time to understand what the results or what the changes in the results are. So you do mostly a lot of experiments and you try to basically discover a new material based on that. But actually you don't know whether you have found a global optimum then. You just do it, as I've said, on a trial and error basis. So you need a lot of experiments. It's also an experience-based approach. So already multiple years ago, researchers thought about that and discovered something or designed a method they call design of experiments, which is another method which you could use in the development of new materials. It's basically a systematic approach on how you design your experiments and statistical analysis in combination. What you do is basically you divide everything. You have input parameters, output parameters, and you build a complete set of experiments based on that. It's a very structured approach, but it's also a complex approach. If you have lots of data, if you have many parameters or variables as input and output parameters, then it's a really complex approach, and it has its limitations. And the, I would say, newest approach we see right now is the machine learning approach. It's not based only on experience. It's not based only on methods. It's based on the data you have collected, the historical set of data, basically, which the system uses to suggest promising candidates in the development. So the idea is to reduce the number of experiments because the system already in the beginning suggests promising candidates, promising recipes to do your experiments. So, as I've said, today we brought an example from the paint industry where we applied machine learning. And in this example, we have a customer, and this customer, his challenges were that he had many recipes, basically, because everything he did was very customer specific, so customer specific colors. And for every development, he had basically like around 50, but more like 100 to 300 experiments with around 100 different recipes. And so you can assume it's cost and time and resource intensive development, shorter projects last 5 months. So for him, it was really a topic to optimize the development of these customer specific colors. The company has collected over the last 2 years, 2,000 recipes. They were grouped, or they had 6 material groups with 150 assigned materials, 8 most relevant performance factors, and also all the corresponding measured values for these performance factors for the different experiments has been collected. So what the company wanted was basically to use this data to, on the one hand, predict how well a certain recipe will perform, and on the other hand, to find an optimum recipe, or at least a recipe that is mostly relevant for a specific target performance. And the aim was to make the previously very time-consuming development process much more efficient by significantly reducing the number of experiments and being able to process basically the customer development, the custom-specific development, the customer inquiries much quicker. So what we did was basically a 5-step approach, similar to what Charles just showed us. The first step was acquiring experimental data. They had, as I said, over 2,000 experiments, which were documented in Excel files. And for each experiment, they had the recipe with the material and the quantity, and of course, also the measured performance values. Everything was documented in that Excel. The next big step was to prepare basically the data and clean it. And here it was a bit of a challenge and much more extensive because the data was not in a way saved or stored in a way that machines could easily understand it. So it was necessary, for example, to normalize data, to remove outliers, but there were also for example, different lines in one cell in Excel, so with different entries. There were names that were not always unambiguous, so it was really a challenge to prepare that data, clean that data, to have a data set which you could really use for machine learning. The third step then, model training. And for model training, we always, first of all, start with understanding the data. Means we plot the data to have an initial understanding of the data of the different variables, and see some first, for example, correlations, things like that. And it's always useful to talk to the application specialists here, so the paint and lacquer developers, to explain the data further after the initial analysis, to get a deeper understanding of the data, which dependencies are already known, which variables are most important. And you take all this information then and can adapt it to the data set, for example, change desired performance factors, etc. And then after all that preparation work and first understanding of the data, you search for models that predict the performance values for the different recipes. And you start, and this is always our advice, to start with the simpler ones first, and then gradually use more advanced models if needed. And you always compare after training the model with the simplest and then more advanced models. You compare the performance of these models and do cross-validation checks, and then you can check which model works best. After having finalized a trained model, we advise always, when deploying the model, to use a tool that's really easy to use, that's user-friendly. So don't do it, for example, in Jupyter Notebook, might be too complex for day-to-day material developers, but use it in a software that's really easy to handle. In our case, we, of course, integrate it directly into our software. So that's then for us the easiest way to provide it also to the material developers when working with the ML models. And last but not least, maintain the model. Of course, you always collect new data. So it's important to keep updating the models, taking this new data into account. And also there, software, of course, helps that collects the experiment data and applies it to the machine learning models. So let's have a look on the results. So what you see here is different models we have tested on the data set. As already stated, there's not only one model here for machine learning, but there are a lot of different models you could use. And if you want to measure the, let's say, performance of a model, the goodness of fit, you normally can use R², which is basically a measure, a variable, a calculated variable, which tells you how good this model fits to the data you have. If the R² is 1, then this would be a perfect fit. And it perfectly predicts then the data you have. If R² is basically a 0, then it can predict nothing in your data. The failure is, so it can be right, it can be wrong, so it can predict nothing, basically. You see here we tested different models. We had, for example, very easy models like linear regression, which has a 0.14, so it's not a very high R². And the best fitting model basically is on the top here. It's a Bayesian neural network, which fitted best with 0.73 R², which is quite a solid, I would say, a solid model. In principle, always, as I've said, start with the let's say, models that are very easy, and then step by step go to more complex models. If you have found a model that fits your data quite well and you have trained it, then the first interesting things that you can do with such a model is better understand the data. As Charles said before, it helps you to identify patterns, correlations in the data. And just to make an example here, what we can see here on that subset of data is there was the question, which material category has the greatest influence on a certain performance value? So we had one specific performance value and they asked, okay, which material category should I look first when I want to optimize this performance factor? And you can see here that binders have the greatest influence to explain the differences in performance factor A, and solvents have the second greatest value to explain differences. So the model is a nice analytical tool and it can help you to guide the development in a specific direction. For example, here in this case, to search for new binders if you want to optimize the performance factor A. At the end, for our use case, we ended up with a machine learning model, which was basically a mix of different models. And that resulted in the best option. Also an interesting factor here. So after using different models, we saw that for specific performance factors, there were different Bayesian neural networks fitted best. So in total, we had three different Bayesian neural networks we used here. And you can see the performance factor on the left table, the performance factor, then the chosen model and the R square. And overall, it resulted then in an R square of 0.73. So 73% of the variance of the target variables is explained by the input variables. And you also can see the prediction errors on the right side. Therefore, these violin representations or graphs are quite nice because they show the mean distribution on the one hand, and you can also see basically how you see on the one hand if it's a normal distribution, but you can also see how big the bandwidth is. For example, performance factor D is a very basically very good fit or very less error, and the others have a bigger error. So it helps you to understand also the limits and restrictions of the model, basically beside the R square, to understand how big the error or how the error is distributed. So what do you do then with all these or with this machine learning model? How can you use it in the material development at the end? And this here is from our use case, an example of how you can work with this model. So you will, for example, have given performance factors you want for a specific paint you want to develop a recipe with your performance factors like adhesion pressure and so on. And here you can enter concrete values, you can enter a range, you can enter you can tell them, please minimize that performance factor or maximize that performance factor. And then he suggests you the best fitting recipes to your given desired target values. And he also predicts, of course, the performance of these values for each of these recipes. That means, as a developer, I first simulate different recipes with my desired target values. And if I found the recipes that fit best, just based on the model, I do the experiments in real life. And by that, I can, of course, reduce the number of tests and experiments significantly, and also correlations between the formulation and performance factors become much clearer and gives me further advice on how to optimize it. For example, search for new materials that I can use. Right. And of course, the model can then also learn by new data. So by every experiments you later on do, it takes this data into account and updates the model step by step. So what were our lessons learned working with machine learning in that specific use case? First, lessons learned, the more the better. Here it's about the data. So the more data you have, it's always better. Of course, you can also work with less data and simulate data, but you can say the advice is always the more data you have, the better the accuracy of the models. Then data cleaning is always a manual effort, and it's time consuming. So collecting the data right in the beginning so that machines understand is always very, very helpful. And that means collecting right means that machines have to understand it and that you collect basically all data from devices you have, because there might be some variables you don't think of in the beginning, but they play a role later on in your machine learning model. So better collect all data. Then go beyond data points. It's nice if an algorithm, let's say, explains you something, but it's always good to have an initial understanding, an analytical understanding of expert knowledge as well, and incorporate it into your model. So don't just think or don't just look at data. No one size fits all, which means basically there's no perfect model for everything in machine learning, but yeah, you have to follow an iterative process to find the right algorithm and train the model for your data. Then what we have seen is that combining models can always improve accuracy, as we have seen in our case with multiple Bayesian neural networks. And last but not least, keep gardening. So machine learning is a bit like software. It's never perfect. You always have to apply the new data to your model. The model will change. The model will find some new correlations or patterns in your data. So it needs always to constantly be updated with new data.
To finish today's webinar, as usual, we want to share with you, more than just the lessons learned and a little bit of what can you do if you want to start with machine learning in your R&D or quality department. So first of all, start with the basics. Define your goal. Define the relevant questions you want to solve or answer. Which challenges could be better solved with machine learning? Before diving into machine learning, this clear objective is very essential. Examples here. If you're in R&D, are there any recurring patterns in our formulations or in our taste data that could help develop new recipes more efficiently? If you are in quality assurance, do historical quality data provide any insights into potential defects or even maybe process deviations? The recommendation here, start with a specific question that is going to deliver a real value. Do not start with the goal of just using machine learning for the sake of using machine learning. Second step, if you want to start after you have a goal, start collecting data. Machine learning is only as good as the data it's relying on. So are the relevant data available? Are they structured? Are they consistent? Many data sets exist in very different formats and systems. And the first essential step here is to do the data mapping or harmonize them at least, harmonize the relevant data sources. Try to identify and clean your data before developing the machine learning model. That's what we said before. It costs a lot of time, but you have to do it. Otherwise, the results are going to be less reliable. Third step, use a specialized software with integrating machine learning functions. So instead of developing your own models from scratch, you should actually use a platform like the one LabV has that is already integrating machine learning in some way, or at least providing the base, the data solution to be using machine learning functionalities afterwards. It's gonna eliminate the need for custom modeling and for the implementation, because if you have the right solution, your data is going to be structured, it's going to be understood, and your requirements are going to be much more easier to implement at the end. And finally, start simple. And not simply start, but start simple. Start with a simple model and iterate. It doesn't have to be deep learning right away. You can use simple algorithms because they usually very often provide very valuable insights. More complex models should only be considered after first successes and first proof of concept. So start with a small pilot project to demonstrate a very clear benefit and then scale further. That would be the last recommendation that we have learned from our different experiences. Now it's your turn to be active. We have here a Q&A function. If you have any questions about LabV, about what we have presented today, don't hesitate to write down using the Q&A feature, and we will answer it right away. The first question would be here. It's been a question that's not only today, but it came in the last weeks and during customer meetings. Like if we look at all the process steps we've been talking about, what is the most time costly? Like where do you have to invest the most time in our 4 or 5 steps, 5 or 6 steps in the process? What's our experience here?
So it depends a bit on where you are. Basically, if you haven't collected any data yet, then you start with collecting your data. This could already take a year, 2 years till you have enough data. Actually, if you want to start with machine learning, so there would be maybe other things which you can do first. If you have already data somehow in an Excel format or in other formats, then you could try to use this data, but then you have definitely start with or check for data cleaning, data preparation. This will take most of the time, so always depends on in what kind of formats, and if basically it's always the same format, then this helps. Then you also could write little scripts to do that. So this would be definitely the biggest ones, and then afterwards working with the data, actually applying different models is more a calculational power topic. So how fast is or how much training time do you need? But it's like more, we're talking here about hours or a day, but not more. So actually the first 2 steps are the most time consuming steps.
We have had the recurring question as well about data formats. Can you guide us through a little bit? You've talked about it, but in our use case, or based on our use case and the other experiences we have, what would be the ideal situation if I have available data already? Is it better to have Word, PDF, Excel files? What is the best starting point? I think we have had that like a couple of times already. People asking the question.
Yeah, you mean which is the best data format to start with? Yeah. So basically every data format that can be easily let's call it accessed, maybe, so where you can get data out of the data format. So if it's like a text, a CSV, an Excel file, even a Word file, everything is easier than a PDF file. The most or the biggest problem where nothing works at the end is a PDF file that is scanned as an image. Then you would need something like an image recognition. This is the toughest job to do. But if you have any kind of data format where you really can, at least if it's in PDF with the OCR functionality, then this could also already be a starting point to get the data out and work with it.
There's a question about which software to use for machine learning. Is there any specific software to use for that? Thank you. Well, first of all, you should use LabV to begin with. because that's what we do. We help you build your consistent and structured, harmonized database to be able to start with machine learning. Other than that, I don't know if there is any software recommendation other than LabV.
I mean, I would say before choosing a specific software, the biggest question is, should I use an integrated software solution or should I use different software solutions? And so what I mean is, with integrated software solutions, you have a few building blocks. You have a building block for basically for the data in the lab, where you store all your recipes or your material data, and of course all your experiment data, like all your measurements. Then there's a software block which you could use for the ML functionality. So to build models, to train models. There was even Minitab was here mentioned
yeah.
exactly, which is a specific for DOE, for example. So the basic question is, do you want like a scattered software solution with APIs, or does it make sense to have it in one software solution? And from our point of view, and that's why we are building LabV as it is that an integrated software solution here for, on the one hand, defining your data model, and later on using machine learning on that data model and providing it to the user who's later on developing new recipes makes the most sense. Yeah, that's why we go for an integrated software solution. Of course, there are also, just for machine learning, a lot of specialized software solutions that are then like standalone, basically, for machine learning.
It seems it was the last question for today. So thanks everyone for your attention, for your time. If you have any further question, if you want to dive a little bit deeper into the machine learning space, don't hesitate to just send an email or go on our website, labv.io. There you can find much more about what we're doing, our software. You can get access to my own calendar if you want. You can have a virtual tour. We're happy to talk to you and see how we can help you. If you're somewhere based in Europe, we will be on different trade shows in the next coming month, March to June, from the European Coding Show in Germany up to the French Lab Forum in Paris. Just check our website. Everything is there, and we'll be happy to see you on our booth as well. Thanks for your attention, and see you next webinar. Bye.
Bye.